So, in this lecture we will see the distributed impedance matching network design. That means, as I said that as we go higher in frequency, particularly after 1 gigahertz, it is difficult to rely on inductors, capacitors, etc. Also in these high frequency circuits, fabricating this ALC, they are also difficult. So, we need to design transmission lines or waveguides for realizing L and C's of that. So, that design is called distributed impedance matching network. Transmission lines are less lossy at higher frequency. So, they are used for this impedance matching network. Now, the impedance matching network, if there is a power transport going on in the main line, that is called main line, and for impedance matching we use some auxiliary transmission lines. Now, that transmission line may be shorted or open, that are called stub. So, I can have an open stub or I can have a short stub. Now, as you see that there is a main line, from that the stub can be connected either in shunt, that topology is shown, or it can be a series stub also. Now, depending on which technology you are using, the series and shunt connections, they are preferred, like in sometimes series or shunt or short or open in various technologies, like whether you are having micro strip technology or you are having strip line technology or you are having waveguide technology. Based on that it is chosen, because in some cases fabricating a short or open is easier, because you will have to make some not through via holes are needed. Also in some cases if you have large openings, radiation may take place. So, based on that you need to modify, but a microwave engineer, once he can design any stub, he can change a open stub to a short stub, etc. if he knows Smith chart well, that we will see today. So, you see this is the open stub and short stub. Open stub means finally the stub at one end it is connected to the transmission line either in shunt or series fashion, the other end is left open, whereas a short stub, the end which is not connected to the transmission line, that one is shorted, then it is called a short stub. Now, this is the single stub matching network. You can see that single stub matching, you have the load, then you have a transmission line portion of length d, and then here you can have after that d either a shunt or a series stub. That stub may be open or short, that stub length is L, and so if you consider that you have a transmission line. So, the load in case of shunt stub, generally we carry the analysis in admittance plane, because the load impedance, then after coming to transmission line you come to a new admittance which we are calling Y, and then you are adding the shunts admittance to that, and then finally after you cross the stub from the left end, if you see, it should look at a characteristic admittance, so that it becomes matched. So, single stub matching network will look like this, that YL is matched to Y naught after the stub and the transmission line is connected. Whereas, in case of the series stub, generally we try to do the analysis in the impedance plane. So, the load is considered as Z del, and then after traversing a distance d in the transmission line, it becomes a new impedance Z and then with the series stub you change that Z to Z naught, so that from the transmission line in the left or source side you see a Z naught thing. Now, so here in both these cases single stub matching network, so here you have only a single stub and the location of that stub, these are the two design parameters. So, D, that means where you are placing the stub, how far is it from the load, that is called D, and then length of the stub, that is called L. These are the two things that you need to design, and the stub's characteristic impedance, stub is the auxiliary part transmission line, that characteristic impedance and the main line characteristic impedance, they are generally taken as same, because generally with a when you have either coaxial line or waveguides, a particular type of guide element is available. So, characteristic impedance generally do not change there. So, overview of stub matching, the single stub matching. Now, if you have the shunt type of thing, so first you will have to plot the impedance or admittance. In case of shunt it is admittance, then then you are moving on a transmission line. So, better draw a VSWR circle. You know that if we can plot a load, then we can draw the VSWR circle by connecting with the center. We have seen that actually moving on the transmission line means you are moving on that VSWR circle. So, then find the corresponding admittance, and for rest of the calculation assume the chart as admittance chart, as I said it is a shunt drawing, shunt design. Then find the intersection points between the circle, that VSWR circle, and 1 plus J beta circle. The minimum distance from the normalized admittance to the intersection points towards the generator, give the distance of the tuning point from the generator. That means, what we mean is, suppose this is our Smith chart. Now, in that Smith chart, suppose I have located up to this, you are familiar, suppose this is my load. Now, I can always draw the constant VSWR circle, and then towards generator in the from the Smith chart periphery I can find that towards generator is this. So, I will move and try to come to this. This is the constant conductance circle, let us say, in the Smith chart. So, there I can come. So, here I can either come to this point or I can continue and come to this point. So, these are the two solutions. In one case I will come like this, in one case like this, another case like this. Now, it is up to the designer, because frequency response of these two solutions will be different. So, from frequency response you can decide which one you will take. Also sometimes construction difficulty etcetera can tell you. Now, after coming here, what happens? That means, this part is given by the D portion of the transmission line, that transmission line portion of the between the load and the stub, that changes this. So, the change in the transmission line, how much transmission line length, that you will read from here, because this one has a chart here in the lambda scale, this one also has a chart in the lambda scale. So, from that you can find out that what is the distance you have travelled, and from that you can find out that what is the D, D is how many lambda. Now, after this you know that after coming here you will have to come to the center of the chart to match it, that is done by the susceptance. So, from here you find out that this point is what is the value. Obviously, it is the admittance seen here, that will be 1 plus some J B value. So, you choose shunt susceptance to be negative of that, that means minus J B bar, and so you choose a stub whose susceptance is minus JB bar. So, that you can do. Now, how you can do that? Minus JB bar means if you have a, let us say, short stub. So, short means what? In admittance 1, that in impedance Smith chart, this is your short circuit. In admittance 1, this is your y is equal to y bar is equal to infinity. This is your short circuit. From here, now find out where is your minus JB. So, this much, this length, again reading from the periphery, you can find out what is the length of the stub. So, all the steps are given here, just whatever we have learned from the Smith chart, from that you can just follow this step. And so, here you can see this whole thing, that first step is locate the YL bar point, draw the VSWR circle, locate the 2 points where VSWR circle cuts 1 plus JB circle, each gives a solution of D, take any one. Obviously, later we will see that you can from frequency response you can find out. Then find these values y1. So, you know there are JB1 and JB2. So, the stub susceptance will be either minus JB1 or minus JB2. For shorted stub, start from short circuit and move towards generator along outer periphery to reach minus JB1, etc. So, please go through, you will understand whatever we have discussed in Smith chart. Based on that, this is for series stub. Here you need not go to the admittance plane. Here first you locate your load impedance, then you draw the constant VSWR circle, as you see that in the Smith chart. The after locating the ZL, after locating the ZL here, then you have drawn the VSWR circle, then this VSWR circle intersecting this 1 plus Jx circle at 2 points, one point is this, another point is this. So, that means from your load towards generator means you can come here or you can come to here. So, there will be 2 solutions for this length, because all this means this length ZL you are moving up to here. If you come, then from outer periphery you find out how much you have come, that will be your D. Now, you are either here or here, you take any solution. So, suppose you have taken this solution here. Now, you find out what is the your susceptance value, reactance value. That reactance value will be, you can read from the scale that okay, this is obviously here it is the reactance is negative. So, minus some value. So, that means this stub, its susceptance, its reactance I will take as positive value, whatever I have got here reactance, negative of that I will take here. And for short circuit, this if it is an open stub, open means at the right end portion. So, from this right end I will now in the outer periphery I will have to move at the desired susceptance point. All this we will see in the examples, because without examples it is difficult, but the steps are given here. So, you note down the steps, and from Smith chart you then know what is the this length. So, you can find it from Smith chart. This is all about single stub matching. Now, this frequency response of single stub matching, you see this same design. Let us say that we have taken some values that D is 0.26 lambda, D means the position of the stub from the load. Say load is the resistive part 60 ohm and another, let us say that some capacitance is there. So, the load is 15.82 plus something. Now, that when it is converted here, this is called Z1. So, Z1 is given. Now, Z2, the stub part, that is a shorted transmission line. Shorted transmission line, its impedance is j z naught tan beta L. Now, tan beta L, obviously this L. So, let us say the design has been carried out at a certain frequency. So, we have a particular lambda that we call lambda naught. So, 2 gigahertz, let us say in this case, if we specify that the design is done at 2 gigahertz, 2 gigahertz means it is 15 centimeter is the lambda. So, all our lambda naught are 15 centimeter. So, when we are saying that d is equal to 0.26 lambda, so our length will be actually 0.26 into 15 centimeter. But at other frequencies, it is not 0.26 lambda, it is some other thing. So, if in at other frequency signal, if we give to this impedance network, there will be some reflections, there will be reflection coefficient that is not 0, that is some non-zero value. So, that we can find out that we express this Z2, which is in terms of beta L. Beta L is the electrical length of the transmission line. That beta L can be beta, you know, it is the phase constant of the transmission line, that is 2 pi by lambda. So, we call it 2 pi by lambda and L is some fraction of that lambda. So, beta L can be expressed as f by f naught. So, when f is equal to f naught, that means that design frequency, if the actual frequency is also that, then it is simply beta L is 2.54, otherwise it is different. So, now you can represent your Z1 and Z2 in terms of that. Now, in the shunt case, the total Zin is this. Now, this at f is equal to f naught, this is Zin is equal to Z naught, but at other there will be some other Zin not equal to exactly Z naught. So, there will be reflection that you can plot. So, we have plotted that in a particular problem, as we have seen two solutions. So, you can plot and you see that solution 1 and solution 2. Solution 1, solution 2, you remember that either you are coming here or here. Similarly, how much is the your susceptance, depending on these two, both the D and susceptance, they are different. So, you can plot, and from this you can see that the, suppose I fix that okay, my tolerable, you see at design frequency 2 gigahertz, the reflection coefficient is 0 for both the solution. But when I am nearby, there are some reflection coefficient. So, there will be some mismatch there, some power loss there. Now, depending on application, you can fix that how much power loss you are ready to suffer. So, that you can see that based on that you can draw a horizontal line. Suppose from this, suppose this is your frequency response, the graph is like this. Now, here this is your reflection coefficient magnitude. You can find out, okay, I will fix that this is my maximum. So, my usable bandwidth for which impedance is valid, that means reflection coefficient is not going beyond this, that means power loss is not beyond a certain level, that this is bandwidth. So, here you see based on where you are putting your acceptable or tolerable reflection coefficient, the bandwidth is different. Now, obviously, we will prefer a wider bandwidth one. So, in this case, suppose if we say that 0.1 is our maximum tolerable reflection coefficient magnitude, obviously, I will choose the solution 2. Whereas, if someone says no, the 0.5 is my tolerable bandwidth, then also I will choose solution 2, because you see that its second part it is going very low. So, based on this, designer will have to decide whether he wants to, how much wider bandwidth he is getting from which solution, that solution he prefers. Another distinction point is what is the size of the stubs etc. he is getting, because these two solutions will have different lengths of transmission lines, different length of stubs. Now, getting larger may be problematic, getting very small also may be problematic because of mechanical construction, etc. So, that time based on other criteria you will have to do, but you have this scientific analysis behind you. Now, what is the drawback of single stub matching? So, you see that if the load is changed, then the stub to be redesigned, particularly the position of the stub is to be redesigned. That means that D will vary, because in the Smith chart, instead of this point, if suppose I am at this point, then obviously my coming here will be different. So, that D will be different. So, changing this is a problem, that from the load, that stub position if it is variable, then you cannot have a single tuner to tune various loads. So, that is the drawback of single stub matching. So, people come up with a double stub tuning, where the two stubs are used, not one stub, but the distance between the stubs, that is called D, that is fixed. This one is fixed. So, stub positions are fixed, load immediately connected to the first stub, then there is D, that also fixed, connected to the second stub. So, what is the design? Design is what is the lengths of these stubs. So, that from here you see a match design. Now, here we have taken shunt stubs. So, you see that we have taken, instead of ZL, we can represent the load as YL. From YL, after adding this thing, so here I will get this YL bar plus JB1 bar will be the admittance here. Then I will have to move in a transmission line by a distance D and come here. Now, you see how this is a double stub tuner in our lab. You can see that this is one stub, this is another stub, this is the load. So, load we are connecting, and this two, and this side we are giving the source. This is the carriage that you have seen, this is the meter where you can observe the whole thing, and this stub, these stubs, their lengths you can change, actually they are foldable. So, you can change the lengths. So, those are the two things that you can vary in a this, I think in your lab also you have this. So, now let us see that what is done. We know this thing, this is the transmission line equation, this we use, that gamma x is equal to gamma L this. So, a movement of distance d along transmission line means, from here you can find out this b is equal to 2 pi by lambda. So, if you put that movement of distance d along transmission line means a 4 pi d by lambda angle rotation along VSWR circle. We have already seen that moving along transmission line, same transmission line means moving along a VSWR circle. So, if this distance d is lambda by 2, then transmission line movement 90 degree. If this movement of 2 lambda by 2, this is 180 degree, 3 lambda by 8, 370 degree. Why I am saying this? That means that when these d's are fixed, generally they are taken like this, lambda by 8 or 3 lambda by 8. So, that means 90 degree or 270 degree. Now, you see the beauty that suppose I have in a Smith chart a constant, this is 1 plus j x circle or 1 plus j beta circle, whatever you call. Now, 90 degree rotation of this, 90 degree rotation of this will be this same circle is here, a reflection 90 degree, which side? That means this one I have this center, I have changed to this center. So, I have gone here, this is called towards load reflection. Now, what is the beauty of this? So, here suppose something was, suppose I was at this point. Now, if I move here, then I will be where? So, suppose I am on this circle. So, basically this movement is towards generator, I am moving because this side is generator. So, from here a movement of D means I will come 90 degree here. So, somewhere here. With this you see the procedure for double stub tuning. You locate your YL dash that you are now familiar, that locate the admittance, load admittance, draw the constant VSWR circle. So, what we do in the Smith chart, we locate, let us say this is our YL bar, then I can always draw the constant VSWR circle as a circle like this, center here. Now, depending on if your D is equal to lambda by 8, that means distance between two stubs lambda by 8, you make it 90 degree rotation, that will be something like this. Move towards generator to cut the rotated circle. So, from your load point you move towards generator to cut the rotated 1 plus JB circle. So, from this actually from here you should be on the constant constant conductance circle and see that you change to cut some point, that means you are on a constant resistance circle, but move and come to either this point, or you can also, if you proceed, you can come at some other point, take any of that. Now, the beauty is when you will be transported by a distance d towards generator, you will come to this point 1 plus JB point. So, what we have done, read the 2 points, take one, determine L1. This point after moving a distance d in the main line will fall on 1 plus JB circle, note 1 plus JB value. So, your second stub, that will be compensation of this JB, that means that susceptance will be minus JB. So, depending on whether it is short or open, you now find again from Smith chart, locate the, if it is shorted, locate the short point, and from short you find out how much to go. So, that I get a susceptance of minus JB. So, that you can get the L2. So, this is inter-stub distance. You see this is the 90 degree rotation of the 1 plus JB circle. Our 1 plus JB circle is this, a lambda by 2 separated 2 stubs. So, this circle after reflection become this. So, you try to come on this circle, so that you know that after this movement of lambda by 2 you will come to this circle, and then from there you, it is a change of susceptance which will bring you to the center. Now, again solution wise you can see there are 2 solutions. So, that is all about that any load, any complex load you can match to any real load by these. Then we will see there is another thing, it is not an impedance matching thing, but it is an impedance converter, it is called quarter wave transformer. Quarter wave transformer means a section of transmission line which is placed between a load and any other transmission line of characteristic impedance Z0. Now, the thing is, it can at the input of this quarter wave transformer you get a transmission match. So, it can match any real load, but it cannot match any complex load. But you do not have any problem, because you know by those stub matching you can make complex load can be converted to real load. So, what is the beauty of this? That suppose between two parts of the network you have two different impedances, they are matched, but they have different. Suppose one is at 50 ohm, another is at 100 ohm, they may be matched. Now, quarter wave transformer can bring these impedance levels together, it is a impedance transformer, it is not a matching thing. Now, any complex it can match any real load. Now, its frequency response is not good, it is a very narrow band converter, narrow band transformer, but with this we can build various broadband impedance matching designs. So, we will see that next in our next ones, that with this quarter wave transformer we will start that those impedance matching network that we have designed, distributed ones, they have a frequency response, and that frequency response is narrow band, means it is not more than 15% bandwidth. But if we want that we have a signal which is having more 15% more, in today's world that is coming up with ultra wideband technology, your signal will be having much more bandwidth, much larger than 15%, 500 megahertz bandwidth, etc. So, there you need that impedance matching network also should be having wide band, but these designs cannot give you. So, that how to design broadband design, that will be topic of our next talk. Thank you.